All right, everyone, the Doppler effect. I will tell you that this equation is going to be the most complicated equation looking that we will deal with all year long. But it's really not that bad if you have a system for breaking it down and figuring out what's going on. So first, let's remind ourselves about the Doppler effect because there's some real important details that we kind of glossed over before, but are now critical when we have to start doing the math. So this is the apparent shift in observed frequency due to the relative motion of the source or observer relative to the medium of transport. Okay? And that's that last sentence here, that it's not the motion of the source relative to the observer or the observer relative to the source, but how each independently is moving with respect to the medium of transport, which for our purposes is going to be the air. Remember also the other fact that the Doppler effect had two different mechanisms. The mechanism for the Doppler effect for the moving observer, remember the wave pattern wasn't distorted, it's just that the observer, because they were moving inwards or outwards, was receiving waves more frequently or less frequently based on whether they were encountering extra waves per second or fewer waves per second by running away, or due to the moving source. And with the moving source, right, in this case if the source is moving to the right, the wave pattern itself was altered, and this is our observer. And it's the distortion in the wave pattern that caused a change in the wavelength, which then was the change in the frequency that was affected. And so the equation, therefore, has to both account for a moving source and moving observers independently and simultaneously. And so that's going to be the hard part about this equation. Then remember apparent shift. We say apparent because the source frequency is not changing through this, just the observed frequency is different than what the source is putting out. And at the end of the day, we'd have to just remember a couple of things. That the observed frequency is going to be greater than the source frequency if either the observer is moving towards the source or the source is moving towards the observer. And the observed frequency is less than the source frequency if they go away, right? If the observer is moving away from the source is moving away from the observer. Keep this in mind because that's going to be our sense check over and over and over again. So here we go. What is the equation? Well, let's just start out with a simple structure of the equation. So here we go. Frequency observed is equal to the frequency of the source times a factor, right? I'm going to fill in what this factor is, and this is the complicated bit in just a second. But let's think about this. If this factor is some number, right? It's multiplied by frequency source. So if we come back here, what's going to be true about this factor if the source is moving towards the observer is moving towards the source? Well, I need frequency observed to be greater than frequency source. The only way that can happen then is if what's in the parentheses is greater than 1. So it's some number greater than 1 multiplied by this is bigger than that. And if they're moving away, what's in the parentheses has to be less than 1. If you keep that in mind, that's going to make your life a lot easier. So here we go, folks. What's in here? Well, we said that we're talking here about apparent shift of due to the motion of the source of the observer relative to the medium of transport. What is the medium of the transport effect? Oh, that's right. That affects the speed of the wave itself. So therefore, what goes here in both the numerator and denominator is the speed of the wave. We're going to call that v wave. And these are going to be speeds. I'm not putting our notation for absolute value around them just to make things a little bit easier, but that's going to be the speed of the wave. So I'm going to put a little key here. V wave equals speed of the wave. In this unit, that's going to be the speed of sound, right? So if it's sound, we're talking v wave. If it's in air, is 331 meters per second plus 0.6 meters per second per degrees Celsius times the temperature in Celsius. But if it's in water, that's a different number. If the wave is a water wave, that's a different number. If it's a light wave, that's different. But here, because we're doing sound, that would be the equation. In air, this is the equation we're using. Now next, what's gotta matter? Well, what's gotta matter here is the motion of the source and the motion of the observer relative to the air. In which case, we're just going to say relative to the ground. We're going to assume our air is not moving. Let's pretend it's not a windy day, because this all gets a lot more complicated if the air itself is moving. But let's not complicate. Let's understand the basics first. And so here we go. If the observer is moving, we're going to put that up here. And if the source is moving, we're putting that down here. And so let's just define terms. VO is the speed of the observer, and VS is going to be the speed of the source. And so now here's the part that makes people get a little confused. What goes between these? Plus minus, and then minus plus. And this is the equation for the Doppler effect. And so our job in a problem is going to be to figure out what each of these 5 variables are, and then we're gonna have to make some choices about pluses or minus based on context. So here we go. Let's say I have an observer. Here's my observer, Ollie the observer, right? Here's Ollie. And let's say I have a source. Let's say this is Sally the source. Okay. All right. And let's say that it is a 15-degree Celsius day. You could do the math, but that's going to be a 340 meter per second speed of sound. And let's say that Sally is emitting a concert A. So she's singing 440 hertz. Which I think is actually pretty close. Remember, that's our school bell, so we hear that sound pretty often. And let's say that Sally is moving towards Ollie, right? So there's the velocity of the source. Let's say Ollie's not moving in our example, so the velocity of the speed of the observer is 0. So how would I set this up then? Well, here I go. I would write down my equation, which I've done up there, and I'd start filling in the parts. So in place of frequency of the source, I put 440 hertz. Speed of the wave, I'm just going to fill in my template, and so that's 340 meters per second. I'm going to put that in both places. Velocity of the speed of the observer is 0, so I'm going to put a 0 there. And the source, let's say Sally is moving at 10 meters per second. All right, cool. And so I always write my equation down, fill out the template with the numbers, and now I make choices about signs. Well, obviously here, it doesn't matter whether I choose positive or negative, because that's just going to be nothing. But what am I going to put down here? Well, that's when we go back to, boom, this. We know, since the source is trying to move towards the observer, that the observer is going to hear a higher frequency than what the source is putting out. So at that point here, if I need a higher frequency, I need this fraction to come out bigger than 1. And so what happens, what do I have to do in order to make this fraction come out to be bigger than 1? Well, I need this denominator to be smaller. And so I'm going to then choose a negative sign, right? Because that makes the denominator smaller. And there you go. If the source is moving towards, well, there we go. I just hit my little apparatus here. Sorry about that. That was a bit dramatic. I'm not going to redo it because we're several minutes into it. Sorry about that, folks. All right. That when the source is moving towards the observer, I'm going to choose a negative sign there. And so then if I plug that into my calculator, it's 440 times 340 over 330. And I think we can see very clearly that that is going to come out to be a bigger number, which is my expectation, right? In fact, it comes out to be 453 hertz, right? And so notice then, as long as all of these speeds are constant and that frequency is constant, the observed frequency is a constant higher frequency than what the source is putting out. Now, I'm not going to do an example for each of these, but let's talk through this. If Sally was moving away from Ollie, I would want down here, away, I want this fraction to be less than 1. I'd want a plus down here. And so I'm going to put that in on our equation here, away. Now let's talk about a moving observer, okay? So now let's say that Ollie is running towards Sally. So there's a velocity of the observer, and let's say Sally is the source, and she is just standing still. So V source is 0, right? Still singing her concert A. She's got good breath control. There she goes. So what would this look like as a plug-in? Well, frequency observed is equal to still 440 hertz, okay? And then I would fill in my template. 340 meters per second, 340 meters per second. I'm going to put 0 down here because it doesn't matter. And let's say Ollie's running towards Sally at 10 meters per second. So I'm putting in 10 meters per second for the speed of Ollie. Now, here's the thing. Ollie's moving towards Sally, so I want this fraction to be bigger than 1. Well, in the numerator, because that's where this velocity is, or the speed is, I would now want a plus, because that's going to make the numerator bigger than the denominator, therefore this fraction is greater than 1, and I can plug that in and see if I get the result that I'm expecting, and I am. I'm getting a larger frequency. It's 452.9 hertz. By the way, this is 453.3 hertz. So interestingly enough, notice Sally moving towards Ollie at 10 meters per second caused a shift upwards of 13.3 hertz. Ollie moving towards Sally at 10 meters per second only shifted it up 12.9 hertz. It's not the same amount, right? And that's going back to the reason because the mechanisms are different. So even it matters whether it's the observer moving or whether it is the source moving in terms of the size of that shift, because the mechanisms are the same, or different, excuse me, right? So notice here I chose positive with the moving observer because I needed this fraction to come out bigger than 1, so there's towards, right? And if Ollie was moving away from Sally, I would want the numerator, I would need this fraction to be less than 1, so the observed frequency is less than the source frequency. I would choose the minus. So going back to why is our equation structured the way it is, and it's for a mnemonic, right? If I write it plus, minus, minus, plus, you don't have to do it that way. I just recommend you write it that way. It's because the top sign means toward. Top means toward. And if you just remember that, you're good. Now, let's talk about what happens if both Ollie and Sally are moving. Like, let's say, for example, Ollie is going to run towards Sally at 8 meters per second. I love you, Sally, I love you. And Sally is like, ugh, okay, you're totally thirsty and I can't. And she's going to run away at 15 meters per second and still screaming her concert A. Why? I don't know. That's her thing, right? Like, that's what all her TikToks are about. But she's like, no, get away from me, you thirsty beast. But of course, she's screaming that using a concert A, 440 hertz. Now, let's fill in our template. So I'll just write the equation again because it's on the other sheet. Frequency observed is frequency source, and it's going to be speed of the wave, plus minus, minus plus, speed of the observer, speed of source. There we go. And so let's fill in our template. So 440 hertz. That's pretty simple. Let's say it's still that 15 degrees day. It's still that same day. 340 meters per second, 340 meters per second. We said that Ollie's speed is 8, so I'm going to plop that into the portion there. And Sally's speed is 15 meters per, by the way, 15 meters per second is ridiculous. Like, she is running, right? That's like 33 miles an hour. It's ridiculous, but let's just go with it. Now, you might want to say, oh, okay, well, here, they're going to move away from each other because Sally is running faster than Ollie. But that's not the right way to think about this. Remember, the two mechanisms of the Doppler effect are independent of one another, right? The moving source distorts the wave pattern. The moving observer means that our observer is either going to hear fewer waves or more waves per second because of the way that they're encountering the waves. So when doing the Doppler effect equation and you're trying to decide signs, you have to pretend that the other thing is not moving. Let me do for instance. So we know that Sally is going to get the hell away from Ollie, sure, but in order to decide the sign here, if Sally were not moving, is Oliver trying to get closer to her or further from her? The answer is closer, which means towards, which means I choose a positive. Sally, if Oliver were not moving, is she trying to move away from him or towards him? The answer is away. And so on the bottom, if I want away, that means I need this fraction, the effect of the denominator to make this fraction less than 1, I would want to choose, once again, the positive. And that would be how I would fill in the signs here. So this is all about independently deciding each of those signs as if the other thing is not moving, because the two mechanisms that cause the Doppler effect are different. And that's the critical thing that I was talking about before that we kind of didn't pay attention to before. It didn't really matter about these mechanisms, but the independence of that analysis that I did was contingent on the fact that these mechanisms are different than one another. Now, you'll notice here that our numerator is less than our denominator, which makes sense because net they're moving away, but I couldn't use the relative velocity of 7 and just pretend only Sally was moving at 7 and get the same number, because you don't get the same number. I'll show you that in just a second. It's not that much different, folks, but it's still different, and therefore we have to do this the right way. Okay, so this gets us a 431.3 hertz. If I just pretended it was relative to each other, this might look like 440, and I won't do the units here because I'm just showing you, and then just the 0 here, pretending Ollie's not moving, and that they're moving away from each other at 7, right? That gets me 440 hertz, 340 over 347, which is a different fraction. So 340 divided by 347 times 440 gives me 431.1 hertz. It's not that much different, but if the numbers were bigger, the frequencies were bigger or whatnot, it could be a huge distinction, but this is just incorrect. So with that, I'm going to ask you to do some problems with Doppler math. Now, actually before that, remember, our equation is only valid for talking about things moving along a line. If instead what I have was here was my observer and my source was moving like this, the geometry is different, the equation is actually also different, and so we want to know that what we're doing here with the Doppler effect is a sort of an introduction to the Doppler effect, and that it is much more complicated as you introduce additional factors on this. But if we can't get the basics of talking about what's happening along a line with people moving at constant speeds, we certainly could never do any variations. Now, our course is not going to have those variations, but I just wanted to be truthful in that those variations exist.